All right, so we're going to talk a lot about how we take scientific measurements and how that factors into significant figures or significant digits, which is a subject that many of you have probably been exposed to. And it amounts to a bunch of rules that you need to memorize and then apply to a given problem. How many significant digits are there in this number? How do you use significant digits when you're doing multiplication and division or addition and subtraction? All right, those are just rules. And unfortunately, you just have to remember those rules. But at an introductory level class like this, you really don't understand why we have those rules. So I'm going to spend some time with you to discuss why it is that significant digits actually matter and why you're learning these rules to start applying them now. And it really has to do with the difference between an exact number and an inexact number. Exact numbers are easy. Those are the ones you can count. I can see that there are exactly 5 rulers on this slide. If I spent the time to count how many of you are sitting here, I would be able to make that count exactly, assuming I don't mess up, right? So there's error in the mess up. But if I can count each one of you, that would be an exact number. There's no uncertainty in that determination. Whereas an inexact number has uncertainty attached to it. And everything that you do in science, when you make a measurement using a scientific device, it has a measurement scale or it has a digital readout, okay? Those all have estimates built into them. There's uncertainty built into it. And that is where significant digits come into play. So for example, let's look at this red bar, okay? This is the exact same red bar. I know because I copy and pasted it in PowerPoint, okay? But I'm going to now measure the distance using 2 different measurement scales. Let's say these are centimeters. Okay. And let's just look at the scale on the top. I can tell based on the markings of this scale that that red bar is greater than 5 centimeters, but less than 6 centimeters. Okay. So I'm going to write down with certainty, I know that this is 5 point something. And I know this with certainty. Why do I know that it's with certainty? Because that number is marked on the measurement scale. There's a 5 there. And I can see that that bar is greater than 5. But I know it's less than 6. So that 5 is certain. But now I need to make one more number in here, one more significant digit that shows the estimate of where that measurement falls between the 5 and the 6. So you might look at that and say, I don't know, what do you think it is? 0.4, 0.5, 0.3, what do you think? 0.3, how many think it's 0.3? How many would say it's 0.4? How many would say it's 0.5? Oh, 0.5. Right, well, there are more hands for 0.4, so I'll put this as 5.4. But notice that we don't really know for sure, right? The ones who raised their hands for 0.3 aren't wrong. This is an estimate, and an estimate has error, okay? The error of this estimate is going to be plus or minus 0.1 centimeters. We know that from the scale that's being measured. When your scale is measured and every unit is numbered here, we can make our estimate to the next decimal place. Okay, so the ones who said 0.4 aren't wrong. The ones who said 0.3 aren't wrong. When we report this number, this measurement scientifically, we report it as 5.4. And if I give it to Sydney, she doesn't know how I made this measurement, but she knows that I made it properly using the scientific method and using significant digits. She'll know not only what the measurement scale was, but she'll also know what the error of the estimate is, because both of these are significant figures. Or significant digits. Significant digits, significant figures, we use those terms interchangeably. Let's take a look at that same measurement now using a more sensitive measurement scale. Now we have markings every 10th of a centimeter. So we can zoom in on this And now, what do we know for certain? We still know that it's 5 because it's clearly greater than 5 and less than 6. Kind of fuzzy. But now I can clearly see that it's greater than 5.3, but less than 5.4. So I know that it's 5.3 with certainty. And now my estimate, because I have 10 markings here, I can make my estimate to one more sensitive decimal place between the 2 markings on my scale. So now both of these are known with certainty. And now we need one more for my estimate. Now, again, I can do a show of hands, but I guess you kind of get the idea there. To me, that looks like it's a little bit more than halfway between the markings. All right. So I'm going to say maybe that's 0.06. Because remember, this marking here, this is 5.3. And this marking is 5.4. So I'm going to say that my estimate is going to be 5.36. That 0.06, that's the estimate. And I can't go any more sensitive than that, right? But that estimate can only be made to one more sensitive decimal place, and that's it. For example, going back up to the top, we said it was 5.4 using that scale. You can't say that it's 5.45 or 5.46. The estimate can only be made to one more decimal place more sensitive than where your markings allow you to be. And that's only, and this is a subtlety, that's only when you have 10 markings between each point. Or each point is marked for every unit like it is up here. But the point being here is that our estimate, it only goes to one more decimal place. You can only estimate to one more sensitive place between the markings. But all 3 of these now are considered to be significant digits. This number reported with this scale has 3 significant figures, or sig figs. Now, I think is it written on a later slide? It may not be. So I'm going to write this out for you. Oh, it's written right here on the top. No, it's not written on the top. So I'll write it down for you here. Your significant digits, okay? This is a definition for you here. So significant figures or significant digits, okay? These are going to include all of the digits that you know with certainty plus one more for the estimate. All right, that's your definition. Let me highlight that. It's very important. Because when we start caring about how many significant figures you're reporting an answer to, that reflects the sensitivity of the measurement that you're making and the uncertainty. We now know that this 5.4 on top, that one was measured, and the uncertainty here is plus or minus 0.1 centimeters. The uncertainty for the more sensitive measurement is plus or minus 0.1 centimeters. 0.01. 0.01 centimeters. Okay. Now, when you start making calculations with your measurements, that's where some of these other rules come into play. And the rules, I'm not going to go over these rules step by step for you. You can read these in the textbook. You can look at about 100,000 different YouTube videos that explain the rules of significant digits and how to use them when you're multiplying and dividing or adding and subtracting. Okay. There's 2 ways to view the importance of significant figures. One is how I just showed you. How do you properly record the right number of significant figures when you make a scientific measurement? And you're going to have a chance to practice doing that in your laboratory exercise, not this week, but next week. You'll be doing a lot of measurements. But then the other part of it is to be able to look at a number that you didn't collect, but somebody else did scientifically, and be able to tell which of those are significant digits and which ones are not. And really, the only trick here is about the zeros. Everything that's not a zero in the number, if it's reported properly, okay? Anything that's not a zero, a non-zero number, that's going to be significant. So that part's easy. For the zeros, you just have to know which zeros are significant and which zeros are not significant. And it's listed for you up here. Some zeros will be significant and some zeros will not be significant. All right, so what's significant? Okay, all non-zero numbers, that's what I just told you. And the zeros will be significant when they're between two non-zero numbers, or if they're after the non-zero numbers when there's a decimal point there. So that's what we mean by a trailing number. So for example, if I give you the number 101, that has 3 significant figures. I'll even abbreviate it by SF. Because that zero, it's in between, it's in the middle. That means that that zero is part of the certainty. When I made my measurement on the scale, there was a zero in there. It's not an estimate. The one, the last one in the ones place, that is the estimate, okay? I can look at a number and I can tell what the scale was and what's known with certainty and what's the estimate. There's 3 sig figs there. A trailing zero is something like this. If I gave you 0.2000, how many significant digits do you think are in that number? How many think it's, I heard 3, how many think it's 3? How many think it's 1? How many think it's 5? How many think it's 4? It is 4, all right? The trick is with the zeros. The zeros that are trailing these, because there's a decimal point there, these zeros are significant. The one in front, the leading zero, this is not significant. And again, I'm just showing you the rules, okay? And first and foremost, you just have to remember these rules. It's a longer discussion and I'd be happy to have it with you, either in office hours or if I see you in lab, to understand why it is that the trailing ones are significant, but the leading ones are not. Yes, question. So it has to do with trailing. Trailing just means that, yes, it's after the decimal, but only they're only significant when there's a decimal there. For example, if I give you this number instead, if I give you 2,000, how many significant figures are in this number, 2,000? There's just one, because there's 3 trailing zeros, but there's no decimal point, okay? They are just holding the place. It's telling you that the 1 sig fig, which is 2, is in the thousands place, all right? So we know about the scale or the magnitude of this number, and those zeros are just there to hold place. Now, a later discussion, we might talk about scientific notation. That's another way to do the same thing, where you just focus on the significant figures and the exponent tells you what the magnitude, what the place value of those sig figs are. Okay, so again, those are just the rules for what's significant and what's not. The zeros are not significant if they're trailing, but there's no decimal. They're also not significant when they're leading. See, this one here, this is a leading. So if I have another number, for example, like this, 0.0020, how many significant figures are in that number? How many think it's 1? How many think it's 2? How many think it's 3? How many think it's 4? Okay. It is 2. There are 2 significant figures because the leading zeros never are significant. They're just showing you the place. However, in this case, the trailing zero is significant because there's a decimal point there. Okay. I'm just exposing you to this now. If this is confusing to you, yeah, I know it's confusing. Go to the textbook, right? Read it up there. Go online, come to lab. We'll be going over this again in lab as well. Sig figs will be covered next week in lab, but that's still plenty of time for you to practice doing this and whatnot before the exam comes up on this, which isn't for a little while still. So don't worry about that just yet. Okay, so the zeros are the tricky part. Then you just need to know the rules for multiplying and dividing, as well as for addition and subtraction. And these rules are pretty simple. I'll just tell them to you. They're written for you up here on the slide. When you're multiplying or dividing, which frankly is the same thing, you simply keep track of the fewest number of significant figures that there are in any given number. That's what you're limited to in what you're reporting in the end. And that's because all of these inexact numbers are coming from scientific measures with estimates. Okay, you are limited by your weakest link, right? The chain breaks based on the weakest link. So the least significant number in all of your measurements is going to limit how significant you can report your final answer to. So for example, if we made two measurements, let's say one was this, 0.0321, and let's multiply that by 4,500, right? It doesn't matter what instruments we made these measurements on, okay? What matters is how we're accurately reporting the number of significant figures. So how many sig figs are in 0.0321? There's just 3. There's 3 sig figs here. How many sig figs are in the number 4,500, the way I wrote it? Just 2. The trailing zeros are not significant. That means that my least significant, or the measurement with the most uncertainty, that's what's going to limit our final answer as we report it in sig figs. So if I take out my little calculator here, and remember in this class, you only need a simple calculator like this. We're not doing much more than multiplying and dividing, adding, subtracting, and using exponents in this class. So 0.0321 multiplied by 4,500. And my calculator says that the answer is 144.45. Okay, now the calculator has no idea of these numbers that I put in, what's significant and what's not significant. So you need to take a look at this. How can we properly report this answer? How many sig figs can we report this answer to? Just 2. We're limited by the lowest significant number. Sorry, we're limited by the lowest number of significant figures. It's the weakest link. We can only report this answer to 2 sig figs. So when you do that, you start with the highest place value, which in this case is the hundreds. So that 1 is significant and that 4 is significant, right? Those 2 places. And everything else is not significant. So we have to apply a cutoff and some rounding. In this case, we cut off where we're going to report our significant figures. And then we need to apply a rounding rule. We only look at the first number that's cut off. We only look at this 4. We don't look at the 0.4 or the 0.5 to determine our rounding. And then we use simple rounding rules, right? If it's 0 through 4, we keep the number in front of it the same. And if it's 5 through 9, then we round up to the next digit. In this case, the 4 that's dropped is going to tell us that we're not going to round up the number in front of it. This stays as 1, 4 for our significant figures. And then we have to put zeros in there for everything else. Because the zeros, we still need zeros in there, non-significant zeros, to hold the place value. We know that this number is somewhere in the hundreds range. If I just report it as 1, 4, that's in the tens range. So I need to put that 0 back here, the insignificant 0, to show that this number is in the hundreds range. Right, but I don't do this. Because what happens if I do this? Now all of those zeros are significant because there's a decimal place there. All of those trailing zeros are significant. And that means that this measurement is really sensitive down to plus or minus 0.01, whatever the units are. When really, we can only make this is really going to be plus or minus 10. Because there's a lot more uncertainty in our final calculation. Okay. Addition and subtraction is a little similar. There, you're not looking at the number of significant figures. There, you're looking at the decimal place. Yes, there's a question. So the question is, why did I stop at the 14 instead of stopping here? Right. And the answer is because I'm looking at the number of significant figures in my two measurements, and I'm limited by the one that has the fewest number of sig figs, and that's 2. So I had to stop at the 2. If I had evidence for 3 being the limiting one, then I would go one more. Absolutely. All right, when we're doing addition and subtraction, it's a little different. Right? Here we're looking at the sensitivity of the numbers, not so much the number of significant digits. So, for example, if I have 2 numbers that I need to add, 3.2 and 45.67, right? First of all, let's just add them up, right? We line up the decimal place, the decimal points, and we add them up. So that's 7884. Okay, let me make that a little neater for you. Okay. Now, how many significant digits are there in the 3.2? There's 2, right? How many significant digits are there in this number? 4. But we don't apply the addition, we don't apply the multiplication and division rules here. If we were, we would say we have to report that number to 2 sig figs. Instead, what we do here now is we're limited by the level of sensitivity. The 3.2 was measured only to the 10th place, whereas the 45.67 was measured to the 100th place. Once again, we're limited by the least sensitive, in this case, measurement. So you line up the decimal places, and what I like to do is just put a little dotted line down here. We're limiting, our cutoff is made by the least sensitive measurement, the one that was only made to the 10th place. That means that our cutoff is going to be, we're going to retain the 8. That's going to be significant, okay? And this 7 is what gets lost. So that one gets lost. It's going to round that 8 up to a 9. So we would report this as 48.9. And again, I'm not using units right now, so whatever the units would be. And then this number would be reported to 3 significant digits in the end, or 3 sig figs. Okay, so it's a little different. And just pay attention to your order of operations when you're doing math. If there's something in parentheses, you always do that first. Then you apply your multiplication and division and then addition and subtraction. Okay, and I'll show you an example of that just here in a minute. So just to remind you, all of this has to do with the weakest link. Ultimately, the number that you're reporting, your calculations, is limited by the least significant measurement that you've made in your calculation. And that's what all of these rules are here for. All right, so I'm going to leave you to your own study then, either in the textbook or elsewhere, or office hours if you need some more help understanding this. And again, you'll see this again in the labs. You'll have more chance to practice there. So I'm going to take you through an example now. And we already did this example in the video content when we measured the density of that gold nugget, all right, by displacement. But now I'm going to come back to this and look at this with significant digits. So I think the numbers that we used in there, let me see. Well, I have my notes written here. I think these are going to be the same. So we started here at 50.0 milliliters. By the way, when you do these measurements in lab and you measure that value is 50.0, those are all your significant digits. Even if your measurement is right on the line and that line happens to be a 0, you still put the 0 in. This is still your estimate, because you're estimating that measurement is right on the line. It could be plus or minus 1.1 milliliter here, okay? But you're reporting it as 0.0. So you don't measure this as just 50. You've got to put that 0.0 in because that's your estimate. Yes. So the question is, if you had a beaker that didn't have all of the lines there, you wouldn't put the decimal. That's a more complicated answer that you'll get to when you take lab, all right? But I'll just tell you now that beakers, even though beakers have volume measurements on them, they are not used to measure volume. You would never report a measured volume from what you read on that scale in a beaker. That scale is only there on a beaker to tell you about how much is there. If you're going to measure volume, you're going to use a graduated cylinder. All right, and then we put the gold nugget in there, and we get, I think in the video it said we had a volume of 58.5 milliliters. So now I'm going to put units. And I think from here on out, I'm going to include units in everything. Because when you report a number in science, you have to have not only the right number of sig figs, but also the correct units. And yes, you will be graded accordingly if you don't put your units in. All right, so we all know what density is, okay? Density is mass divided by volume. And we're given the mass in this problem. The mass was 164 grams. Now, what's the volume that's displaced here? The volume that's displaced, we got that from the difference in the volume in the graduated cylinder here. That was 58.5 milliliters minus 50 milliliters equals 8.5 milliliters. So that's our volume. Okay. So if we were to calculate the density then, the density is going to equal 164 grams divided by 8.5 milliliters. And we put that in our calculator. 164 divided by 8.5. And I get 19.2941175 grams per milliliter. Now, what's wrong with that? Too many digits, right? The calculator is stupid with respect to what's significant and what's not. All right. So how many sig figs can we report that number to? I heard 2 and 3. How many think it's 2? How many think it's 3? Okay. Why is it 2? What's that? Weakest link. So because there's 2 sig figs in the 8.5. But wait a minute, a lot of people said 3. So someone who said 3, why is it 3? Go ahead. That's right, because the 50.0 and the 58.5 had 3 sig figs. All right. So let's line this up. Let's put the whole thing into play here. The whole thing would be 164 grams divided by, and let's put the whole thing in here, 58.5 minus 50.0 milliliters. If you do it this way, you might think, oh, well, the weakest link is 3 sig figs. Everything here has 3 sig figs, right? The correct answer is 2 sig figs in your reported answer, because when you follow your order of operations, you always do what's in the parentheses first. And when we do that first, we get 8.5 milliliters. Then when we're doing our final calculation, 164 divided by 8.5, we're now limited by the 2 sig figs, because by the addition rules in the parentheses, we can only report that number with 2 sig figs. So that's what goes into that calculation. It's a bit of a subtlety, but I wanted to show that to you. Yes. Oh, the 164 was given. It's not shown on the slide here. It was given in the original example that's in the video. So I'm just using the same number there. Okay, so we want to do this first. Parentheses. So there's only 2 sig figs here, which means our cutoff is here. And we don't need to worry about the 9 and the 4 and the 1 and the 1. We only need to focus on the first digit that's dropped, and that's a 2. So the 2 does not round that 9 up to a 10. So we would report this as 19 grams per milliliter. Okay. Now, one final note on this topic. I mentioned scientific notation. We'll talk more about that probably when we get there in lab. so I don't want to spend too much time on that now. But scientific notation is a really good way to emphasize what's significant and what's not, instead of having to remember all these rules. In scientific notation, you have some number. Let's see. Let's say I did a calculation and my calculator spit out this number, 0.0024867. Now, depending on how many significant figures we're allowed to report that number to, let's say that in the calculation, let's say we knew that we needed to report this to 3 sig figs. So what would that number look like as 3 sig figs? 0.00, those are insignificant, so we don't need to worry about that. The first significant digit then in the highest place value is the 2, and then the 4, and then the 8. So we're going to cut it off here for 3 sig figs. The 6, we don't worry about the 7, just the 6, but that's greater than 5, so that's going to round that 8 that we're keeping. It's going to round that to a 9. So we would report this as 249 to 3 sig figs. If I were to put that in scientific notation, I would write it this way: 2.49 times 10 to the negative 3. And what that's doing, there's 2 components to scientific notation. The first part is what we call the coefficient, and that has all of the significant digits. And the decimal is after the first significant figure. Right, that's called the coefficient. So that's telling me right there, there's 3 sig figs in this number. It's the 2 and the 4 and the 9. By convention, you put the decimal place after the first significant digit, and then you have the exponent factor of 10. That just shows you the place value, the magnitude of this number. We know it's 10 to the minus third, so this number is in the range of the 10,000ths. Sorry, the thousandths. Sorry, it's just 3 decimal places. To the thousandths range, 0.001 to 0.009. Question? Why is it minus 3 instead of positive 3? Because 10 to the minus 3 is equal to 0.001. 10 to the positive third would be 1,000. And again, a more thorough answer for that we can take care of in office hours. Yeah, if any of this basic math that I'm kind of blowing through real quickly here, I'm doing that because you are all expected to have an understanding, a very firm understanding of these concepts. And if you don't, then come to office hours. There's going to be tutoring set up at the tutoring center soon enough that will help you with these things as well. But you do need to have command of these basic mathematic abilities to then not focus on, so you can focus on the more complex chemistry stuff that's going to be sitting on top of all this. All right, but let's say we needed to report this instead to 2 sig figs. Well, if it's 2 sig figs, now my cutoff is going to be after the 4. So now I look at the 8, and I would report this as 0.0025. And in scientific notation, that would be 2.5 times 10 to the minus third. There's only 2 sig figs here, and now the rounding has changed a bit. And what if we only wanted to report this as 1 sig fig? This is a little trickier. So now my cutoff is here after the 2. I only look at the 4 for rounding. What I don't do is say, oh, well, there is an 8 there, and the 8's going to round that 4 up to a 5, and then that 5 is going to round my 2 up to a 3. That's not what you do, because by the rules of significant figures, those rules are in place because they are reflective on the sensitivity and the error of your scientific measurement. And if the error in your scientific measurement only allowed you to report this as 1 significant figure, that means that the 8 and the 6 and the 7 aren't significant at all. You don't know that that's an 8. That could have been a 2, in which case the 2 doesn't round the 4 up to a 5, and so on and so on. So you only look at the 1 decimal place more sensitive of where your cutoff is for your rounding. So in this case, you go back to the original number, and this 4 that's being dropped now does not round the 2 up. So this is reported as 0.002, not 0.003. It's how you apply the rules and then where you apply your rounding at. And of course, if this were in scientific notation, we would write this as 2 times 10 to the minus third. There's only one significant digit there. Yes, question. Is there a time? Yeah, of course there's a time when you would round this. Well, no, you wouldn't, because these zeros are insignificant in this example. There are examples where you would round a 0 up, yes, but that would be when the 0 is a significant 0. Yes.
You can't say 2.0, right?
If you were to say 2.0, that would be incorrect, because that would mean that decimal point makes that 0 significant. Okay, so that's why you can only report that with a 2 if you're reporting it as 1 sig bit. It's a great question. Students will do that all the time because we want to put that decimal point in there. It's just, you just want to do it. But if you're paying attention to significance, if I were to do that and put a 0 there, that 0 after the decimal becomes significant. And then that's not correct for this setup. Okay, so last topic is an important one. Let's see how far we get here. There's a few examples I have. We may not have time for all of them, but you'll be doing this in laboratory as well. This has to do with unit conversion and dimensional analysis. Many of you have probably learned how to do this in various ways earlier, and I'm going to show you a convention of doing this methodically. And if you learn this, it will save your life. It will not just save your grade, it will save your life someday, right? It is a process. And if you do it methodically and slowly and write out all your units and pay attention to everything, it will always lead you in the right direction. And it will show you when you've made a mistake. And I'll just tell you, before I even show you this method, when I see mistakes on exam questions that have to do this, and students don't do it properly, they get messed up. And they don't even know they're getting messed up. They're just jotting numbers down. They're not keeping track of units. They're not organizing them in a way that tells them that they've set the problem up right or wrong. So here's the process. And I'm going to show it to you with this problem right here. We're going to calculate how many seconds there are in 1 calendar year. And so we don't have to worry about significant digits here. I'm going to make this as 1.00 years. And the way we do this is we always start with what's given. What's given is 1.00 years. We're going to consider that that's our measurement, okay? So we're going to start with 1.00 years. And I'm going to put that in parentheses, and I'm going to now apply a series of conversion factors. Conversion factors are simply the same value being measured with different units. In this case, I'm going to measure years. Instead of in years, let's measure it in I don't know, we can do it in weeks, we can do it in months, or we can do it in days. Let's just skip ahead a little bit. We'll do it in days. So how many days are there in 1 year? What is it? Either 365, or some of you might want to say 365.25. Again, that depends on your measurement. Now, this is a little trick here, okay? When you're looking at a conversion factors are considered to be exact conversion factors. We consider them to be exact numbers, all right? So 365.25 days per year. This is an exact number. Our measurement is an inexact number, meaning that that has significant digits. But exact numbers, those are our counting numbers, all right? There's no uncertainty there. All conversion factors are exact numbers. So in other words, we don't pay attention to sig figs here as far as our rules. So these don't affect the sig fig rules. Now, I've set this up with a clear division sign. There are 365.25 days per year. Per means divided by. And I've set it up this way so that I can show that the units cancel out. Units in the numerator here will cancel with units in the denominator here. And that leaves me with units in the numerator of days. So if I just stopped here and I took my calculator out, I'd be able to calculate how many days there are in a year. Of course, we already know that that's our conversion factor. But now let's take it further because we want to go to seconds. So my strategy here is I'm going to go from days to hours per day, and then I'll go minutes per hour, and then I'll go seconds per minute. And each step, I'm going to set this up as a conversion factor. All right. In every one day, how many hours are there? 24. Again, this is a counting number. It's also a conversion factor. Whether I count it as 24 hours or one day, it's the same quantity. All I'm doing is changing my units. I'm converting my units from days into hours. So that's mathematically, I set it up this way so that days in the numerator here cancels with days in the denominator here. Now, if I were to calculate this number, whatever it is, that would give me how many hours there are in one calendar year. But we need to go further than that. We need to go from hours into minutes and then minutes into seconds. So when you're doing this analysis and you're not exactly sure what the next step is, just take a look at the preceding the preceding value, 24 hours per day. We want the units to cancel. So I know that my units in the denominator need to cancel with the units of the numerator. So hours are going to go in the denominator, and I'm going to convert that into minutes. Now I know that my units will cancel. Now, what are the numbers associated with those units? 60 minutes in 1 hour. So the 60 goes with the minutes and the 1 goes with the hour. Make sure that you do it methodically this way. Put your units in first so they cancel, and then attach the right number to the right unit. Now we'll go from minutes now are in the denominator, so they cancel out. And we're going to convert that into seconds. Finally, we're where we want to be. There's 60 seconds in 1 minute. And now we can calculate an answer. And whatever that answer is, we know that the units are going to be in seconds because I've methodically lined everything up. And do it with a horizontal division bar. Don't, if you're in the habit of using a slash, all right, and lining everything up with like a, minutes per hour with a slash and whatnot, it will get confusing. You really want to be clear about what's in the numerator and what's in the denominator. Now, some of you set it up kind of like this. That's fine. However you want to set it up is fine, as long as it's clear numerator and clear denominator, so that not only can you show yourself if you've made a mistake, but on an exam, if you set it up this way and you make a mistake, if I can see that you've made a mistake in your analysis, chances are you'll get a lot of partial credit for that, maybe even full credit, depending on what the problem is. Because otherwise, you just calculate some crazy number that your calculator spits out and it's wrong. I can't tell why it's wrong if I can't see your work. But if I can see your work, I'll give you credit if I can, or partial credit if I can. But it also shows you if you've set it up correctly and allows you to make a correction in there. All right, so when I plugged this into my calculator back in my office, I got the number, my calculator told me it was 3.1557600 times 10 to the 7th seconds. And that's a pretty big number, but you'd expect it to be a big number. That's the other thing you should do. When you do a big calculation like this, think about, should the number be really big? Should the number be really small? Because sometimes if you just believe your calculator and you plugged it in wrong, even though you thought you did, but the calculator thought you did something else, you get a number that doesn't make sense, you might want to rethink how you plugged it in or how you set things up. So how many sig figs can we report this to? 3? Why not 1? We got 1 hour, 1 day, 1 minute down there. Say what? How many think it's 3? How many think it's 1? But nobody can tell me why it's not 1. Oh, why 1? See, I tried to misdirect you to the 1. Yeah, if you look at the 60 up here, how many sig figs are in that 60? There's just 1. Right? But the answer is to 3 sig figs. Why 3 sig figs and not 1? Because yes, it's because of that, but why not the 60? Why not the 1? Why doesn't that factor in? It's because it's a conversion factor. That's exactly right. Conversion factors are considered exact counting numbers. There are exactly 60 minutes in 1 hour. There's no uncertainty there. So we don't factor that in, all right? That's, let's just highlight it. This is why we don't look at the conversion factors for our determination of what's significant in the end, okay? We only look at, usually it's only what's given in this case, but you have to pay attention, all right? What's given is 3 sig figs. So that's what we're going to report our final answer to. This 5 rounds that 5 up to a 6. So we would report this as 3.16 times 10 to the 7th seconds. And actually the units for seconds is just an S. So there you go. And then be nice and put a nice box around your answer. Okay. Here we got time for one more set of questions here to practice this on. Jet fuel. It's measured using mass, but it's dispensed by volume. It's kind of interesting. If you're in aviation, we don't measure that by volume, but we're given the density. All right, here's the density, 0.80 kilograms per liter. So let's use dimensional analysis. What's the mass of 77,000 liters of jet fuel? Now, normally I would let you guys loose and try to play with this a little bit yourself. There's not enough time, and I want to get to the end of this to show you these examples. So I'm going to just solve these for you and explain it, all right? But follow along carefully. What's given here? We do have 2 things that are given. You're given a density and you're given a volume. Okay. Well, the mass is what we're going to calculate. But what we're given is we're given this volume of fuel. We're also given the density, but here it's something per something else. This is a conversion factor. So the way to tell the difference of what to pay attention to is usually what's given isn't something per something else. So you always start with what's given. Let's put that down, 7,700 liters. And we want to convert that into a mass. Now we're not told what the units are, so we'll put this in kilograms. Maybe we'll put it in grams. I don't know. We'll see. Actually, we'll probably put it in grams. So first, we're going to use the density as a conversion factor. So this is what's given. We're going to use density as a conversion factor. Instead of just writing it in there, I'm going to put the units in first. We want to make sure that the units cancel in dimensional analysis. So I'm going to put liters in the denominator, and we're going to convert that into kilograms. Now, it turns out that happens to be exactly how density is set up, right? But this is our conversion factor. There's 0.80 kilograms per 1 liter, okay? And we get an answer out for that. 7,700 times 0.8, and I get 6,160 in my calculator. That's kilograms. How many sig figs can I report that answer to? 2. There's only 2 sig figs in what's given. So we make our cutoff here. We report this as 6,200 kilograms. It's to 2 sig figs. If I were to write that in scientific notation, it would be 6.2 times 10 to the 3rd kilograms. But now let's work it backwards. What's the volume of 8,100 kilograms? All right, so let's start with 8,100 kilograms. Now this is our given. We're going to use the same conversion factor, but now it's going to be the reciprocal of density because we need kilograms in the denominator and we need liters in the numerator. So now the 0.80 goes down here and the 1 comes up here. Okay. If I plug that in my calculator, I get this number, 10,125 liters. How many sig figs can I report that answer to? To 2, right? Because there's 2 sig figs here. So what's my answer going to be? So you want to report it as 10,000? What's the problem with that? If I report this number as 10,000, how many sig figs are in the number in red? Just 1. But we know that we should be reporting it to 2. We know that this 0 is significant, but these are not significant. So if I just reported that answer as 10,000, that's wrong. So how can I report this number that correctly shows the right number of sig figs? Say what? 10,100? Well, if I did that, now the 1 and the 0 and the 1 are significant. That's not the right answer either. How can I report this number correctly? Yes. One 1.0 times 10 to the 4th. But the point here is that in scientific notation, remember the coefficient part shows you the number of sig figs. That shows us that there is 1 0 there. That first 0 is significant, but the other ones are not. And then the 4 is showing you the place value. This number is in the 10,000s range. All right. Now, for those of you who aren't quite comfortable with what the exponent should be in scientific, right, spend a little bit of time reviewing that on your own, or come to me in office hours or in the tutoring as well. All right.